muchas gracias. Unfortunately, my Spanish is bad, so I will be obliged to speak in English. Thank you very much for the kind introduction. Before starting with my presentation, I would like to warmly acknowledge you, the organizers of this wonderful event, for inviting me to deliver this lecture. I'm honored and very happy to be here to contribute to this summit. So, as it was introduced, I work as an assistant professor at Northwestern University in Chicago in the United States. And I also serve as the chief executive officer of an engineering consulting company that was co-founded with my colleague, Professor Louis, director of the Soil Mechanics Laboratory at the Swiss Federal Institute of Technology in Lausanne, to develop a technology that we call energy geostructures, as well as systems that represent networks of this technology, in an effort to positively revolutionize urban environments. So today, with my presentation, what I will try to do will be to gather the scientific engineering activities that we are carrying out to foster the diffusion of energy geostructures and geosystems worldwide. But now the main question is, what are energy geostructures? And so let's start with the presentation. So as all of you might know, soils represent probably the oldest means that have been used for storing and capturing heat. Just think about so-called ice houses that were used to store ice at shallow depths in the subsurface in order to preserve it, thanks to the fact that the temperature at shallow depths remains relatively constant throughout the year, being warmer than the ambient temperature during winter and cooler during summer. Then, as you also probably know, as for sure you know, geostructures actually represent probably, again, the oldest means that has been used for sustaining structures. So energy geostructures basically resort to the two previous principles. Actually, energy geostructures leverage the two previous principles by equipping pipes, typically made of polyethylene, within reinforced concrete structures containing a heat-carrier fluid that circulates into them. And this actually allows to achieve a favorable heat exchange between the ground and all types of built environments, so that conventional structures such as pile foundations, retaining walls, and tunnels can be transformed into so-called energy piles, energy walls, and energy tunnels. So that's the novelty. And again, the concept is relatively simple. It's based on the fact that the temperature at shallow depths remains relatively constant throughout the year. And so what we are actually doing with these energy geostructures is to harvest the energy that is present at shallow depths for applications that include, for example, the heating and cooling of buildings and infrastructures. So what we get in practice are these kind of structures in which you can see pipes that are mounted along the reinforcing cage of piles to transform them into so-called energy piles. Or you can deal with so-called energy barrettes and walls. And again, there you can appreciate the pipes installed along the reinforcing cage of these structures, in which the heat carrier fluid will circulate, exchanging heat. And this heat carrier fluid typically is water. So again, the principle is simple, and as all simple principle, it works, the technology works pretty well. And you can also have other types of energy geostructures, such as slabs, as well as tunnel segmental linings, for example. So again, what you can get are those types of structures here. You can have both deep foundations and shallow foundations, as well as energy infrastructures, such as tunnels. But what's the relevance of this? So, as it has been highlighted, the building sector substantially contributes to the world final energy consumption. Depending on the country, from 25 to 45% of the global final energy consumption is associated with the building sector. And if you zoom in this contribution, again, depending on the country, you can appreciate that from 50 to 80% of the energy we consume in buildings is actually employed for their heating and cooling, thus for space conditioning, as well as for hot water production. So it's a massive amount of the energy we consume is actually employed for the heating and cooling of our environments, as well as for the production of hot water. Now, The main issue that we currently face is that the global energy market has been and is still dominated by the use of non-renewable energy sources, and in particular by the combustion of fossil fuels that, as we know, lead to consequences such as environmental pollution and more extreme and unusual climatic events that are triggered by the combustion of fossil fuels and the release in the atmosphere of CO2 emissions and greenhouse gases in general. So by harvesting shallow geothermal energy, which is a renewable energy source, energy geostructures allow us to avoid this problem and to sustain in an environmentally friendly way human activity needs. In particular, there are plenty of opportunities around the world to develop these systems. In Europe, thanks to the Energy Performance of Building Directive that basically promotes the development of so-called nearly zero energy buildings, that these buildings that, among other features, harvest local renewable energy sources. And this is also present in the United States with similar initiatives. Such a concept has been further pushed forward in France through the development of so-called BPOS buildings, so positive energy buildings that actually produce more energy than what they consume during their operation. So all of this means that basically, almost irrespective of whether is your geographical location, there are incentives to apply these technologies. And what are the applications? So, well, the applications of energy geostructures are broad. They include heating and cooling, hot water production, de-icing, and thermal energy storage. So, as you can see, the first two applications basically meet the energy needs that were recalled previously. And there are also additional applications, including de-icing and underground thermal energy storage, because that are particularly favorable. De-icing applications are particularly favorable because we can avoid the use of salts to de-ice structures and infrastructures such as road pavements and etc. And this is a critical advantage compared to conventional approaches resorting, for example, to mechanical systems or salts that in the long term will reduce the resilience of these structures. And the applications of energy geostructures for underground thermal energy storage is particularly favorable in several conditions where we can use the ground as a thermal battery. So the idea is that we store thermal energy there that will be used in the foreseeable future for given applications that include, for example, heating and or cooling. Now, as you can infer, the fact of merging multiple roles in a unique technology includes unprecedented scientific and engineering challenges. And so today I will try to address a number of these challenges. In this slide, I am particularly summarizing from a scientific perspective what are some of the challenges involved with the analysis and design of energy geostructures. In the slide, you can particularly see so-called master equations or governing equations that describe the development of heat transfer, mass transfer, as well as the equilibrium of bodies. And as you can see, basically, several variables appears in different equations, highlighting that a coupling between phenomena such as heat transfer, mass transfer, and deformation. That is to say, heat transfer can trigger mass transfer, the opposite is true, but heat transfer and mass transfer can also influence the mechanics of materials. So basically, when we design and analyze energy geostructures, there is the need to consider all of these coupled aspects. In particular, the energy performance of energy geostructures is governed by the thermohydraulic behavior of these structures, which depends on phenomena such as heat transfer and mass transfer. And in this context, of course, we need to deal with different materials, such as the ground, the air in the context, for example, of tunnels, as well as the material that is used to constitute energy geostructures. And here there are a number of phenomena that occur that allow us to have this energy harvesting. Typically, we have a convection heat transfer that occurs due to the circulation of the fluid in the pipes. Conduction heat transfer within the material that constitutes energy geostructures that typically is reinforced concrete. And then conduction or convection in the ground, depending on whether a limited or significant groundwater flow is present. Now, a key feature of energy geostructures such as energy tunnels is that in addition to being capable of harvesting energy from the ground, with energy tunnels we can also harvest energy through the air that is present in tunnels. So as it was introduced, basically when train brake, they release heat. People waiting for getting the metro release as well heat. There is the influence of the waste heat present at shallow depths due to the buildings and infrastructures present therein. So there are a number of influences that modify the temperature field, not only in the ground but also in the air, and that can be used for the energy harvesting. And these are some of the aspects that must be considered for the energy analysis and design of energy structures. Now, when we deal with the geotechnical and structural performance of energy geostructures, because as you can infer, we must analyze and design them to be able to sustain the loads coming from buildings. First, we need to deal with the mechanical loads, and this is something that is conventional, and we need to deal with, for example, mechanical induced compressions of our structures. While when we deal with the energy harvesting, we expect to have temperature changes that will modify the behavior of these structures and must be considered again for the analysis and design of these structures. In particular, the energy harvesting of energy structures will lead to thermal expansions and contractions of both the structures as well as the surrounding ground. Okay? Now, the key implications of all of this is that we are dealing with a multi-physical and coupled behavior. And because of this, we need to develop fundamental theoretical and experimental competence as well as prediction tools to be able to analyze and design energy geostructures. So this has actually been the goal of Professor Loria and myself over the past several years. So to develop competence that will allow to massively establish and develop energy geostructures around the world. So today, among the various possible topics that I could treat, I have decided to focus on the analysis and design of so-called energy piles, as well as on the analysis and design of so-called energy barrettes. And I will do so with respect by considering a case study that we worked on at Geoeg, our consulting company, in a recent period. That is this project here located in Principality of Monaco. The project actually includes this tower, and even though it's not pictured there, there will be an additional tower, as well as this building down here, including 150 units of state housing, an international school, a creche, and a multi-floor underground parking. Here you have some features of the project. So actually, the project is located in a very dense urban environment. The construction of this building is extremely complex. It gathers several construction phases, several types of structures. This was the construction state last summer on May 2019. And actually here you can see, for example, the installation of an energy barrette in the ground. This is actually a 70-meter deep energy barrette. So it's almost like a high-rise building itself, the barrette that sustains the building, in which you can see the pipes mounted along the reinforcing cage that, as I told you before, will contain basically water that will circulate into them, allowing to exchange heat with the ground. And so, as you can expect, even though today I will only focus on the analysis and design aspects involved with energy geostructures, there also are very important challenges related to the realization of these structures that must be considered properly for a successful application. Okay. Now, in the context of this project, a design of a complete energy foundation has been developed. In particular, the foundation gathers energy barrettes, energy piles, and energy walls. And in the following, I will expand on some features of these foundations. This is a schematic of the stratigraphy of the site, in which you can see that there is an unsaturated area and a saturated area, where the main challenge there is actually to ensure an optimal performance due to the fact that when dealing with unsaturated ground conditions, the energy performance will be a little bit lower than under saturated conditions, and then this is related to the physical properties of water, for example, that is present in the pores of the soil. So we dealt with massive square meters and numbers of energy piles to supply renewable energy to the considered building. So when we focus with the analysis and design of energy piles, as I told you before, there are a number of challenges that need to be considered. The typical energy problem actually involves the circulation of a fluid into the pipes. So that's the critical difference compared to conventional pipes. Okay, so we have pipes with a heated fluid that circulates. When we target the heating of buildings, we inject a fluid that is cooler, that is colder than the temperature in the ground, and will actually come out of the ground warmer for the heating of the building. And the opposite will occur when we will cool buildings. So we will typically inject a fluid that is warmer than the temperature of the ground in order to cool it down and use this temperature for the cooling of buildings. Okay? Now, as soon as we deal with pipe configurations, there is the challenge in this context to define what are the best pipe configuration. And this is a key aspect. Although it might seem a very relatively simple engineering aspect, it actually strongly governs the energy performance of energy piles, such as other energy structures. In particular, and I will try to prove you the following through the result of numerical simulations that we carried out for this purpose, and that we typically carry out in the context of our projects. In this slide, you can appreciate over time the evolution of the thermal power that can be harvested through an energy pile in some given conditions. As you can see, only depending on the pipe configuration, so for the same site condition, a different pipe configuration can give you a variation of up to 40% of the energy yield that comes from the same pile in the same conditions under the same exploitations. So that's a major aspect. If you can imagine that the system of energy structure that you design might give you 40% more of the energy that you could expect, this is for sure something that must be considered properly in analysis and design. Often, what we see is that people don't think that energy structures are easy to apply, or they don't provide sufficient energy. Well, based on our experience, there are very few cases, if any, in which energy structures are not applicable and are not effective. If designs of this technology will not give an appropriate energy yield, probably it's because the design itself was not carefully executed. Okay. Now, when we deal with the typical geotechnical and structural problem involved with energy pile, this is what happens. So what happens is that compared to the evolution of forces along the depth of piles, the same evolution caused by thermal loads associated with building heating or cooling is profoundly different and must be considered for analysis and design. What happens in particular is that due to the fact that the piles will be restrained by the presence of the ground, thermally induced stresses and strains will be developed, and these stresses and strains must be considered for the geotechnical and structural analysis and design of these geostructures. A further aspect that comes into play is that when energy piles and piles in general are located sufficiently close to each other, they interact with themselves. And in the context of energy piles, actually we have group effects caused by both mechanical and thermal loads. These group effects actually induce a higher group deformation under the same average load, as you can see in this slide, that basically shows for a group of 4 piles in which only one or all of the 4 energy piles are activated, the increase in vertical strain per unit temperature change. And at the same time, you have a decrease in the stress that develops in the piles due to the presence and influence of group effects. Now, so what we typically deal with when we deal with energy piles is something like this. So we have foundations that expand, that affect the slab that typically connects the piles. These will induce mechanical interactions with piles that might not operate as heat exchangers located in the surroundings. Then we typically have a heat diffusion that might affect piles located nearby that will also expand their own. So all of these aspects must be considered for the geotechnical and structural design of energy piles. So to address these problems, there are, of course, a number of ways. What we developed in this context and what I will talk about in the following will be analytical models that can be used for this purpose. So in particular, we developed two theoretically sound analytical models that basically simplify energy pile related problems to a single equivalent pier or a pair of piles, and actually allow us to get the overall deformation of energy pile groups in an effective way. And so in the following, I will just briefly focus on some features of the so-called equivalent pier method. The rationale of this method is that any general energy pile group can be modeled as a single equivalent pier, characterized by the same average length of the piles in the group, as well as by an equivalent diameter and some equivalent thermomechanical properties. And what this model actually allows to do is to get the vertical deformation of any group of piles that might be subjected to mechanical and thermal loads. And for example, here you have a prediction of the vertical strain that was observed in a group of 4 energy piles with depth when these piles were subjected to a temperature change of 10 degrees Celsius. Okay, so that's typically a simplified yet rigorous theoretical approach that can be applied in practice to analyze and design energy pile foundations. Okay, and this closes a little bit some of the aspects that must be considered for the analysis and design of energy piles. So from one side you have the energy aspects, and from the other side, although everything is integrated, you have the geotechnical and structural aspects. Now, before I told you that basically the influence of thermal loads should be considered in design, so since recent years, the main question was when and how. So when and how should we consider the influence of thermal loads? Should we consider them from a structural and geotechnical design perspective at ultimate limit states, so when dealing with failure-related conditions, or only at serviceability states, that is, when dealing with deformation-related conditions? And so what we did in that context was actually to prove, based on theoretical considerations, that the influence of thermal loads should be considered only at serviceability limit states, because these loads only affect the deformation of energy geostructures and energy piles in particular. So I would now like to step into the analysis and design of energy barrettes, which are actually, as you have seen, pile foundations that are used to sustain typically tall buildings, very tall and heavy buildings, in situations in which the use of piles is not sufficient. Okay. Again, here the first aspect that needs to be considered is the pipe configuration. As you can see, depending on the pipe configuration, you can have a tremendous change in the thermal power that can be harvested through these energy geostructures in the same site conditions. Okay. Differently to energy piles, as I showed you before, when dealing with plain energy geostructures such as barrette, we can have these structures completely embedded in the ground. So the heat exchange primarily occurs between the ground and the energy geostructure. But you can also have interfaces with air. And in that context, you also have convection heat transfer that develops and is typically proportional to the velocity of the air that flows adjacent to the structure. Okay. So in the following, I will just focus on the first case for conciseness sake, in which heat transfer is governed by conduction and is developed when energy barrettes are completely surrounded with the ground. So to do so, again, I will use the results of numerical simulations that we carried out with reference to the considered case study. These simulations actually include the modeling of the heat and mass transfer that occur within the piles, but also within the barrettes, but also in the surroundings of the barrettes. And to get complementary information, I will also expand on the results of some experimental tests called thermal performance tests that can be used to basically quantify what is the thermal potential of a given site and what is the energy output that we can expect from actually any possible type of energy geostructure. And in this slide, you have a comparison between typical numerical and experimental results that can be obtained through these approaches. In particular, you can see over time the evolution of the inlet and outlet temperature from the energy barrette. Such information being critical to understand what is the thermal power that we can harvest through energy structures, as well as for a more comprehensive of the ground conditions and the ground properties. So in this context, again, in order to give you a sense of what was the influence of the pipe configuration with respect to the case study, we carried out numerical simulations through a model that was basically validated through the experimental tests. And you can see that basically only by varying the pipe configuration in this way, we can have approximately 16, so up to 20% of change in the energy that can be harvested from the same barrettes. And this, again, from an energy perspective, if you multiply this result by 60 barrettes, as in our case, the result is substantial in terms of energy that you can save, okay? Similar to piles, when we deal with barrettes, if they are located sufficiently close to each other, we can expect them to interact. And these interactions can be both mechanical and thermal. So this is a typical result of numerical simulations that could be used to address this problem, in which you see that as a function of time, you actually have thermal interactions that develop and will have an influence on the energy performance of your system. And so for this reason, should be considered in analysis and design, okay? Other aspects related to energy barrettes and plain energy structures is that they are subjected, similar to piles, to mechanical loads, and often to flexural loads that induce moments, okay? So in contrast to conventional structures that are only subjected to mechanical loads, in this case we also have the application of thermal loads that cause thermally induced bending moments and curvatures and stress variations, and must be considered again in analysis and design. So similar to what I have proposed you for the case of piles, in the following I will very briefly expand on an analytical solution that we developed to basically investigate what is the influence of mechanical and thermal loads applied to plain energy structures, where the concept in this case is actually to simplify, to decompose any relatively complex system of plain energy structures into a simpler system represented by a beam resting on an elastic soil, in order then to get, for example, evolutions of the shear forces or bending moments or all the other internal actions that can characterize your structures, and that should be considered in analysis and design, okay? So until now, we have pretty much focused on the application of energy structures at the local scale of buildings. However, even if I will only briefly touch on these aspects, you can consider to apply energy structures at the district and city scale. So the beauty of the technology is actually that it can be connected into networks to function as energy supply providers, okay? So basically we can assume to work with tunnels, for example, that will provide energy not only for their heating or cooling, which are usually very limited because we don't typically need a substantial amount of energy in tunnels, but we need this energy for the buildings that are located at the surface, okay? So you can imagine to get this energy from there and bring it to buildings and have systems that connect multiple energy structures. So in this context, we are carrying out different studies with a focus on tunnels, trying to see what is the feasibility of this energy harvesting at the discrete scale. What are, for example, the radiuses of influence around tunnels within which the energy supply is favorable from an economic perspective, in addition to, of course, a physical perspective, okay? So, to conclude, what I have tried to convey to you is that energy structures really represent, in our opinion, a powerful technology to sustain human activity needs with a limited impact on the environment. You have seen that there are broad possible applications: heating, cooling, hot water production in several applications, de-icing, and thermal energy storage. Not only these geostructures can be applied at the building scale, but also at the district scale in the form of so-called energy geosystems. And so I think this technology will really contribute to make the ground and the subsurface as a new, actually probably is the oldest means, but as a new spatial and resourceful means to contribute and to sustain our needs that are just thanks to just something that is below our feet. Okay, so more and more attention, as it was highlighted in the introduction, will be paid and should be paid to what is present below our feet. And this is one of the technology that can be used to harvest energy from the ground. Now, actually, the day after tomorrow, this book that we have written together with Professor Loria will come out. So for the people who might be interested in this topic, we hope that there you will be able to find some useful information. And for those who might prefer to have verbal discussions about this topic, next year in March we will develop the third edition of a short course about the analysis and design of energy geostructures, to which you are all invited. And with this, I thank you very much for your attention. Muchas gracias.